Hi everyone, this lesson is about the graph of a rectangular hyperbola. This is our general equation for the hyperbola. Remember, A is the vertical dilation factor, H is the horizontal shift or the vertical asymptote, and Y is the vertical shift or the horizontal asymptote. More about that in a minute. So to begin with, we'll set up some sliders for the values of A, H and K. Now you've seen me do this before, so I'll just pause while I do that. Okay, so I've just set up my three sliders there for the value of A, H and K. Now to do my hyperbola. So I'll literally be entering this equation. So Y equals A over X take H plus K. Now at the moment, with the sliders set the way they are, Y is, I see, I typed in Y instead of A. That's better. Now with the sliders set the way they are, it's not much of an equation, it's really just the graph of 0. So I'll set the value of A equal to 1. Now my graph is, if you like, the most fundamental hyperbola. It's the graph Y equals 1 over X. No value, 0 for H and 0 for K. As we can see here, imagine X equals 1, and I substitute 1 over 1, I get a Y value of 1. That's easy. If X equals 2, then I substitute 1 over 2, gives me a Y value of 0.5. So the Y value is decreased. If X equals 3, the Y value is 1 over 3. Alternately, if the X value is 0.5, then 1 divided by 0.5 gives me a Y value of 2. So we get this lovely sharp curve. Now, as I continue going to larger and larger values of X, like say X equals 10, the Y value is 0.1. If I was to move across to X equals 20, 1 over 20 is 0.05. If I went all the way out to X equal to 100, somewhere, then the Y value is 1 over 100 or 0.01. I'd have to zoom in a very long way to see that, but I can start to see that the Y value is, it's not 0, there is a little tiny Y value. In fact, no matter how far I go, the Y value will always be it's getting smaller and smaller, but it will always be a positive number greater than 0. So that graph will run all the way along there, getting closer and closer and closer, but never actually reaching the x-axis. Likewise, we have a similar situation here. As we get closer and closer to 0, dividing by smaller numbers, 1 divided by a small number gives a very large answer. Now, of course, it's forbidden to divide by 0. There is no point on the y-axis. If we put 1 divided by 0, if we try to let x equal 0, then we all know 1 divided by 0 is undefined. So this vertical axis here, the y-axis, actually is a discontinuity on the graph. There is no point there. As soon as we jump to the left, though, dividing by negative numbers gives negative answers. So we see this lovely mirror image of what we saw up in the first quadrant here in the third quadrant. Now these lines, which the graph approaches but never reaches, are called asymptotes. And the horizontal asymptote, actually it might be easier if I just move this a little bit. The value of H, if I make the value of H 5, then all of a sudden I have the formula 1 over X take 5. Now this time I could put an X value of 0, because I end up calculating 1 over negative 5, which is negative 0.2. But I couldn't put X equal 5. If X equaled 5, I'd end up with 1 divided by 0. So this vertical forbidden line, the asymptote, has now lined up here on 5. And I can do a vertical line if I write X equals H. And that turned out to be blue. I think I might make it red, so it's right there. My vertical asymptote now is in line with the value of H. The value of K, let's move K up to 5. Let's put H back to just a different number 3. This time I've got the plus 5 here at the end, and that's just a straight out vertical shift. Every point that used to be there is now pushed upwards by 5, including the horizontal asymptote that used to be on the x-axis is now up here. And I can put a horizontal line if I write y equals k. And so there are my asymptotes. I might make them dotted lines rather than solid lines. Now those asymptotes are going to be controlled by h and k, but the general shape of the graph is staying the same. It's the same shape that it had earlier. So compared to this point here, this point is, if you like, the origin has been shifted to the left by 5 units by h and vertically by 1 unit by the value k. But still, compared to here, it's 1 step forward, 1 step up, or 1 step left, 1 step down, 2 steps forwards, 1/2 of a step up, 3 steps forward, 1/3 of a step up, and so on. So that is, if you like, the anchor point for my graph. Now, what about the value of a, the vertical scaling factor? Just think of this point here for a moment. This point here is 1 step above the asymptote. If I make a equal to 2, then I've suddenly stretched this to be 2 units above instead of 1. The point that used to be here at 1/2 a step above the asymptote is now 2 times that, or 1 unit above. If I stretch that one up to 3, then the point in line with here, which used to be 1 unit above, is now 3 units above. The point at 3, which used to be 1/3 of a step, is now 3 times a third, or 1. The point that used to be at 1/2 is now 3 times 1/2, or 1.5 steps above. So the value of a is doing the same thing that it always does, even in other functions. It scales the vertical axis, and in this case it multiplies them the other way. If I go to a equal 0, then 0 times any y value is still 0, so that's really just the graph of y equals 1. But if I go negative, things start to go upside down. As we've seen before, the value of a is a vertical dilation factor. So that's how we do a rectangular hyperbola. So I'm just going to save that now so that I don't lose it. Hyperbola. Okay, thanks for watching.